Hello, students. We've made it. We made it to the end of the content in this course. We're finally doing the last chapter in your book. This is chapter 13, Annuities, all about helping you learn how to plan for retirement. So let's jump right in. Your book talks about two kinds of annuities. The first kind is the ordinary annuity. This is the kind that you use to save money for retirement. So, just reviewing the definition, an ordinary annuity is an account into which a sequence of equal regular deposits are made and that receives compound interest on those deposits. And then to make the formula doable, we are assuming that the deposits are made on the same schedule that the interest compounds. So, we'll look at an example. We'll look at a few examples to sort of see how that comes up in actual problems. And so, in addition to this definition, we get this ordinary annuity balance formula, which looks like this. And so this is reminiscent of some of those compounding interest equations that we saw in the previous slides, and in the previous chapters. But let's just go through what everything means here. So T, we see T, this is the balance at time T, and it is equal to, all right, this expression. And T shows up in the exponent here, and that's time in years after the initial deposit. So that's the same as what we saw in chapter 12. R is the annual interest rate as a decimal. So again, this is like the same as in chapter 12. N is the number of times per year interest compounds. So this is going to be exactly the same as before. Now here's something new, this payment. So this PYMT is short for payment. It's a new variable, and it is the amount of each regular deposit. So in an annuity account, I mean, the setup is really, all right, you've got a rate, you've got a compounding schedule, you have, you leave it in for a certain amount of time, but you are continually making payments into this account and you're not taking anything out. So this is an account that really is building up money to give you a cushion to save for retirement. And so this PYMT, that's the amount of money you're putting in every time it compounds. Okay, and then this B of T, this is the balance after T years. So let's do an example. I've just brought over the definition of an ordinary annuity and the formula for an ordinary annuity. So let's look at an example. Suppose you found in your budget that you can save $250 per month. And the best rate you can find on an ordinary annuity account is 4.1% that compounds every 4 months. And if you go with this account, what will the balance be after 10 years? So our first job when doing any of these problems is just to organize the information that you know. So T, what's the time in years after the initial deposit? Well, we're assuming we want to know the balance after 10 years. So our T is going to be 10. What's the annual interest rate as a decimal? All right, it's this 4.1%. Converted to a decimal is 0.041. N, the number of times per year that interest compounds. I want you to stop and think about this for a second. Pause it if you need to. How many times per year is the interest compounding? All right, it's tempting. Well, I guess I see students often tempted to say 12 because most of the time interest is compounding monthly and your N is going to be 12. But in this case, N isn't 12 because it's not compounding monthly, it's compounding every 4 months. So then I see students very tempted to say something like, well, maybe 4. But no, if it's compounding every 4 months, 4 months is 1/3 of a year. And so it's compounding 3 times a year. So our N is 3. Now, actually, this is a little bit artificial. don't think I've ever seen an account that actually compounds every 4 months, but this is just to get you thinking, get you realizing that it doesn't actually have to be every month. It can be a different schedule. And I mean, quarterly is probably more common than every 4 months. But okay, in theory, the compounding schedule, yeah, doesn't need to be every month. And so I just set up an equation or set up an example where it's not every month, it's every 4 months, in which case your N is not 12, it's 3. All right, and then what's your payment? The amount of each regular deposit. Again, stop and think about this because might be a little tricky. All right, I'll direct you to this comment in the definition, this final comment. The deposits are made on the same schedule that the interest compounds. So it's tempting to say your regular deposit would be 250 because that's how much you're saving each month, but you're not compounding each month. You're compounding every 4 months. And so you're saving 250 every month for 4 months, that's $1,000. So actually the payment here would be 1,000. And then, all right, what's the balance of the account at time t? This is something you need to calculate. But we've organized all our information, so now we kind of just plug away. So we've taken all of these numbers and put them into the balance formula. We get something like this. And so, all right, it seems like all the hard work is done, except that in my experience, it's very easy to just get this wrong in your calculator. So it's really, there are two battles here. The first battle is organizing your information correctly, in particular, making sure your N and your payment. That can be a little bit tricky. But then the second battle is actually getting the right number, even when you've got everything organized correctly. And the author of your textbook actually made a really nice video about how to use wolframalpha.com. It's a free website that has robust calculating capabilities. And so your authors made a very nice video about how to successfully use that to calculate things like this. So I strongly recommend going and watching that video, and maybe even watching that video before finishing this. But okay, if you successfully put this in your calculator, and I strongly suggest you pause right now and try to calculate it yourself to check to see how, if you're being careful enough. But if you are, you should get $36,000, $778.54. Okay, let's do another example. I'm just going to keep this formula here for reference. All right, suppose you really want to retire in 30 years. And at that time, you want your annuity account to have accumulated a $500,000 balance. That's what you think you're going to need to live comfortably in retirement. Okay, suppose you again choose this ordinary annuity account, same one as before. It's got a 4.1% annual rate and it compounds every 4 months. And now we have two questions. One, how much do the regular payments need to be to get you to that goal? So how much do you need to be putting in every 4 months in order to get that $500,000 balance? And then, all right, how much would you actually need to be saving each month to do that? So again, our first step is to organize. Our time in years after the initial deposit, well, we're saying we want to retire in 30 years, so that's how long we're going to keep this account. Annual interest rate, that has not changed. That's 0.041. The number of times per year the interest compounds, that has not changed. It compounds every 4 months, so it's going to be 3. The payment, the amount of each regular deposit, actually, we don't know. This is something we're going to need to solve for. So, okay, this is a question mark right now. This is what it's asking. What is the regular payment? So, okay, we'll leave that alone for a moment. And now the balance. So in the previous example, we had to solve for the balance. But here we're assuming we know where we want to end up. We know we want a balance of $500,000. So our B of T is going to be 500,000. All right, now that we've organized all our information, let's put it into the formula. And so we get something like this. 500,000 equals 3 times our payment divided by 0.041 times 1 plus 0.041 divided by 3 raised to 3 times 30 minus 1. And here, in my experience, some students start to panic because, all right, we've got this expression and payment is in there, but how do you solve for payment? And that's what we're being asked to do. We're being asked to solve for the payment. So let me walk you through the steps that I think will make it easier if you're not comfortable just doing this all at once. So first, I would recommend taking this expression on the right, this 1 plus 0.041 divided by 3 raised to 3 times 30 minus 1, and just calculate, excuse me, just calculate that first. And so if you plug this into your calculator or Wolfram Alpha, now your expression is 500,000 is 3 times payment divided by 0.041 times, all right, this number ended up being 2.392852. I just took a boatload of decimals here just so I didn't have to worry about rounding errors. All right, I'll just keep a bunch of decimal places. All right, now we're in a better position. Now, okay, in order to find the payment, we've got to isolate it. So we should divide both sides through by this 2.392852. And then we should divide both sides by 3 to get rid of the 3 on this side. And then we should multiply both sides by 0.041 to get rid of the 0.041 on the right side. And if we do that all right, then we've got that the payment is going to be this $500,000 times 0.041 divided by 3 times 2.392852. So I strongly encourage you to do this on your own and make sure that you end up in the same place and you understand why we get this expression for the payment. But then once you're there, plug it into your calculator and you should get $2,855.73. And now let's take a moment and remember, what did we just calculate? This payment is the amount that you are putting in on the compounding schedule. So this is what your regular payment is going to be every 4 months. And what most people are interested in is really how much do I need to save every month in order to be able to make those payments? Because that's really where your budgeting comes in, is on a monthly basis. And so if you need to make a deposit of $2,855.73 every 4 months, then each month you should be saving $713.93. Okay. Now, the other form of annuity that your book talks about is a payout annuity. So whereas the ordinary annuity is a savings account that you are saving up to retirement, the payout annuity is an account that pays out during your retirement. So the definition, a payout annuity is an account that pays out equal payments each period over a specified amount of time, while the remaining balance in the account continues to earn compound interest. So the idea is, okay, sure, maybe you saved your 500,000 or 700,000 or some, large chunk of money over 30 years, you've saved that. You don't just take it all out at once. You want to pay yourself like a monthly wage, basically, during your retirement. And if you're doing that, you want the money that you still got saved, you still want that to be accruing interest. And so the payout annuity formula looks like this, which is slightly more horrific than the ordinary annuity formula, but most of the components are the same. It's just rearranged differently. So T, once again, all right, so it shows up here and here. This is the time in years in the life of the account. R is our annual interest rate as a decimal, so that's the same, except now it's showing up in more places. N, the number of payouts each year, that's your compounding schedule. Um, and that's going to be N, which, okay, shows up in more places, but it's the same N as before. The payment, all right, we're thinking about the payment slightly differently now. So in the ordinary annuity account, the payment is the amount of money you are putting in each month or each period. The payment in a payout annuity formula is the amount you are taking out of the account each pay period. And then P is the amount of money the account starts with. So this is the big difference. One big difference is your ordinary annuity account. You start with nothing, you make regular payments, and then you build up to a large sum. In a payout annuity, you start with a large sum. That's your P. Your account starts with a large amount of money, and then you periodically take money out until you get down to zero. Okay, let's do an example. Suppose you are nearing retirement and that you've saved $500,000. And the best deal you can find on a payout annuity account has an annual rate of 5.8% and pays out every month for 20 years. So if you go with this account, what will your monthly payout be? Well, we've got our payout annuity formula, and let's organize our information. So T, the time and years of the life of the account. Well, you're wanting the account to pay out over 20 years, so our T is going to be 20. What's the annual interest rate as a decimal? Well, the account is 5.8%, so that decimal is 0.058. N is the number of payouts each year. This is an account with monthly payouts, which is honestly the most common. So since the payouts are monthly, it's happening 12 times a year. The payment, the amount you are taking out each month, that we don't know. That's what we're solving for. Say, okay, we've saved up this amount. If I want to live off of this amount for 20 years, how much am I getting each month? So we don't know yet. So we'll just leave that alone for the moment. And then P is the amount of money the account starts with. So that's the money you had saved up in your ordinary annuity that now is going to be the seed money for your payout annuity. And that's that $500,000. Putting all of this in to the formula, we get this nightmare. Yeah, it looks terrible and certainly looks tedious, and I'm not going to lie to you. This is going to be a little tedious, but it's doable. So, all right, we see this again. Maybe we're in wild panic mode because we've got to solve for payment, which means we got to isolate it. How do we do that? Well, take it in steps. My strategy is to go for this fraction here. There's a lot going on, but calculate this first. Maybe you calculate it by taking the numerator first and then dividing that by the denominator, or calculate the numerator and the denominator separately and then divide. Or maybe you plug this whole thing into your calculator or Wolfram Alpha. But I would say a good first step is to turn this into just one number. And if you do that, and I strongly encourage you to check your work on here, or to do it yourself and then check your work against the slides. I got 0.0685637. And again, I just carried around a bunch of decimal places because I just didn't want to worry about rounding errors. All right, now it's just a matter of solving for payment. Again, we got to divide through both sides by this 0.685637. We got to divide through both sides by 12, and we've got to multiply both sides by 0.058. If we do that, we get this expression for the payment, and now it's a matter of plugging this into our calculator appropriately, which I get $3,524.70. And so what this is saying is that, okay, if you saved $500,000 for retirement and you want to have that money pay out every month for 20 years, then, all right, if you get an interest rate of 5.8%, which sadly is way higher than things really are right now, but it's not, I mean, it's not crazy to think that by the time you're ready for retirement, rates will be higher. But okay, you find a rate of 5.8%, and you had that initial amount of the account being 500,000, then you will get a payment of $3,524.70 every month for 20 years. And then at the end of 20 years, there is no more money in the account. So if you think you want the payout to last longer, you might fiddle with the time here. But okay, this is what we get. We would get this much every month for 20 years. So what are the takeaways? Well, an ordinary annuity account, that's the account that helps you save for retirement. It starts with nothing, and you just put money in over time on a regular schedule, and you end up with a large chunk of money, ideally. The payout annuity, that's the account that pays out the money that you saved. So it starts with a large amount of money, and then you take out money on a regular schedule over time, and at the end of the payout period, there's no money left. So it starts with a large amount and ends at zero. And that's it. So, yeah, good job making it to the end of the term. And hopefully you found this all helpful.